is called the Ritz or Rayleigh-Ritz method. So the Ritz method utilizes a quadratic functional referred to as the weak form. Okay, so again, we haven't introduced any discretization yet, but once we introduce a discretization, then we can apply the Ritz method piecewise on every element, and that is the finite element method. So the finite element method is the piecewise implementation of the Rayleigh-Ritz method, okay, on a mesh or discretized body. Okay, so let's talk about the weak form. So there's any differential equation we can derive a weak form for, and there's a 3-step process to doing it. So it's the same 3 steps. So if you ever, this is really the benefit of learning how to solve like this method and solve. It's so powerful because if you can use this, you can use a computer, you can code it, you can solve any problem in any engineering discipline. Right? So what we're going to do, step 1. So step 1 is the same as the weighted residual method. So we're going to take our model equation, and what's the first thing we did when we developed the weighted residual method? Multiply by a test function, right? And then integrate over the body. So I'm going to write down both steps, right? So we'll multiply by a test function. We'll always, I guess the real first step is to move everything to one side of the equation. So we'll move everything to one side of the equation, multiply by a test function, integrate over the body. Step 2, integrate by parts. Somebody's taken a finite element class before. So notice this term here, we have this derivative out here, and so we're going to basically use integration by parts to move that derivative onto the test function. And that will also generate a boundary condition as part of that integration by parts. Go back and look at your notes for a review of the integration by parts formulas if you need to. So I'm just going to write down the solution here. So that's the integration by parts, that's the integral, but then also we have a boundary condition. Step 3, impose the boundary conditions. So, take a look at this. What is this here? That thing there is equal to that over there, at least at x equal to L. So I can basically plug in, I can take Q of L and put it in right there. Right? The other thing is, well, again, we're gonna come up with a more systematic way of choosing these test functions, but let's assume for now that the test functions are chosen such that they obey the boundary conditions, right? And this goes back to the same as in our variational statement. You remember we said that the endpoints, the variations are fixed, right? There is no variation at the boundaries, right? The variation is only sort of in the domain, right? That goes back to the lecture on calculus of variations, right? Since they're, so this is evaluated at L and at 0. So at L, we have that Q of L goes there, right? And at 0, we have a fixed boundary condition, right? U0 equals U of 0. And so there's no variation at the boundary, so that the variation itself is 0 at U equals 0, right? It's fixed. So there's no variation, it's 0. And so what we ultimately end up with So what we end up with is so this is the weak form. Also known as the variational form. Okay? So why do we call it the weak form?
We reduce the differentiability of the solution, like to get a problem like more.
We've weakened.
Yeah.
We've weakened the continuity requirement, right? So look at the original equation. In strong form, I have, if you distribute the d dx, you end up with d squared u dx squared. So you need, u has to have two derivatives, right? By shifting that d dx term onto the test function, now we only require that u has one derivative and the test function has one derivative. So we've weakened the continuity requirement of the solution. Right? The other nice thing that we've done is look at the a of x term, right? Now imagine in your head, I won't write it down, but imagine in your head, a of x is like permeability over viscosity, right? You're solving the steady state diffusivity equation. And you have a permeability field that's spatially varying, right? So it's k of x, right? So if you leave it in the strong form, you have to compute the derivative of k of x, right? However, if you use the integration by parts, it's shifted onto the test function. Now this a of x term is out here, and you don't have to compute a derivative. Right. The other thing to note is like about boundary conditions. So we've used the boundary condition, but I haven't talked about or given them names. So notice that this when you do the integration by parts, you generate this boundary condition, and it actually looks, this guy right here fits right in there. So I can impose the boundary condition into the equation we're solving. Right? And so this type of boundary condition is called a natural boundary condition. Right? It's also called a Dirichlet boundary condition, but I like to think of natural because it kind of naturally fits into the solution, right? So this, just to go back, this is a natural or Dirichlet and this then is an essential. Oh wait, that's not right. This is a Neumann boundary condition. This is a natural or a Neumann. And the way I remember that is they both start with N. That's why I like natural, because natural makes sense to me. It naturally goes into the weak form, and if I can remember natural, then I can remember Neumann, because they both start with N, right? Over here, we have that this is an essential or a Dirichlet. Boundary condition. And I tend to call them essential and natural because they just, in my head, they make sense to me. Again, I've already explained why natural makes sense to me, because it naturally fits into the weak form. Essential, the reason I like to think of it as, use it as essential is because ultimately, when we have this set of equations, we're going to choose some functions for del u, and we're going to use our normal approximating function for u. U is equal to the sum of some basis functions times ui's, or plus basis functions times ci's. So ultimately, when we do that, we compute these integrals, just like in our previous example, weighted integral example, we're going to end up with a set of algebraic equations. And ultimately then, you'll end up with something like this, right? So you have a coefficient matrix times some unknowns, right? And this turns out in the Ritz method that we're developing, this coefficient matrix is singular. And the way to make it not singular is to impose the natural boundary condition, right? The essential boundary conditions. That's why I think of them as essential. You can't solve the problem unless you oppose essential boundary condition.